afternoon, everyone. My name is Asad, and this is my final presentation for Physics 422 Nuclear Physics. The topic of my presentation is, although a topic that might seem a little boring, that is alpha decay only, but I have turned it into a fancy term that says that alpha decay is an application of quantum tunneling, theoretical proof of Geiger-Nuttel's law using Gamow theory. Now, what is alpha decay? In order to dig into the details, we will have to look into the superficial knowledge first. An alpha decay is kind of a nuclear reaction, a spontaneous nuclear reaction in which a large-sized nuclei disintegrates into a daughter nuclei while emitting a particle that scientists at first termed as alpha particles. Those alpha particles later on turned out to be regular helium nuclei. They have very low penetrating power and they can ionize their surroundings to a great extent. They can be shielded by just one thin piece of paper. In fact, the strongest kind of an alpha particle that has ever been found was found in perhaps 1930s, and it penetrated up to 23 centimeters in air. Scientists were dazzled, and they were like, what kind of alpha particle is that? Rutherford, the person who did most of his initial work that led to nuclear physics, used alpha particles, and even he was dazzled. So he later on realized that alpha particles are not the only kind of particles that are decayed in that manner. And that was actually a hydrogen nuclei. Okay, now we get it that whenever a nucleus gets fat enough, it spews something out. But why? Why is that so? Why does it need to spew something out? Like, was it not fine by itself? As it turns out to be, it was not. It was not fine by itself. You see that the general equation for that reaction is given over here. That says that if you have a particle, let's say a parent nuclei named X, and it has an atomic mass of A and an atomic number of Z. Now this particle will disintegrate into a daughter nuclei, and if it is a regular, conventional, orthodox alpha decay, the daughter nuclei will have an atomic mass 4 units less than its parent nuclei, and its atomic number 2 units less, resulting into an emission of a particle that at first we named as alpha particle. Later on we found out that they are just helium nuclei, having their atomic mass 2, having their atomic number 2 and atomic mass 4. Well, these are some superficial things that you must know about alpha particles before diving into the detail, but why? Why but why? Why does it have to disintegrate? Like, this question always dazzled me. So I looked into the details and found out that your answer is really interesting. You see, our nucleus, if we look into a regular, let's say a Bohr atom, we see a nucleus in the center and electrons orbiting the nuclei in a definite orbit. Although this is not a correct description, like these are actually probability clouds, but for the sake of simplicity, I'm going to say that. The electrons are held in their orbits because of an electrostatic or electrodynamic force of attraction between your positively charged nuclei and your negatively charged electron. Okay, that makes sense because, you know, positive charges always attracts negative charges, and when we have same kind of charges, they repel each other. It makes total sense, and it should happen, but then again, we see that a nucleus is a very tight species. It's a very small body, so small that we actually measure it in the order of femtometers. It's ridiculously small. So how come those protons stay together, are glued together so tightly? Well, we looked into the details of the nuclei, and after some rigorous mathematics and beautiful experiments, we found out that there are actually four forces of nature. One of them is strong nuclear force, and I will call it S and F. You see, this strong nuclear force is ridiculously strong. So strong that it can hold those positively charged protons all together. It doesn't matter how much they repel each other using their conventional Coulombic force. Strong nuclear force just overcomes it, as if it's an elephant and Coulombic force is an ant. Anywho, there is a downside of this particular force. It is very, very short-ranged. So what? So what if it is short-range? Nucleus is a short kind of a body. It is a small body. But it turns out to be, even though it is not a problem for regular-sized nuclei, but when its mass exceeds the value of 190 AMU, it gets tricky. It gets a little tricky at that point because your strong nuclear force is very, very short range, and because of that, your Coulombic force start getting the better of it in the long run. So what happens is that your nucleus, let's say that this is your nuclei, we zoom it in, we zoom this thing in, and we find out that this is your nuclei. It spits an alpha particle out of it. Alpha particle out of it. It spits it out. Now people say, why alpha particle? Actually, alpha particle is a very stable kind of a nuclei. We have read the golden numbers of nuclei and it follows one of them. But yeah, it's not the only particle. As I explained earlier, they did observe a proton emitted out of it only. Yeah, so alpha particle can be emitted. In fact, it is the one that is being emitted most of the times. Now, why? Again, why? You see, the alpha particle is actually emitted to achieve stability. And it makes sense. After it emits an alpha particle, its size is reduced. Its Coulombic force that was bugging that nucleus from the inside is not bothering it anymore. So yeah, that's great. It's great for me, works for me. But it turns out to be, there is this one slight little problem. There is this one teeny tiny bit of a problem. Do you know what's that? It's almost impossible for an alpha particle to decay out of its nuclei. Your regular laws of physics just do not allow it. For example, let's imagine that I am jumping out. I'm trying to jump and trying to escape the field of gravity. Now, as far as my velocity will be less than the escape velocity of Earth, there is no chance that I would escape its gravitational field. Right now, it's impossible. But it still happens. Why? Then again, why? Well, because quantum physics. If something doesn't work, go quantum. Yeah. You see, imagine that we have this ball, and there is this energy barrier of height h. The energy that you are providing, the kinetic energy that you are providing this ball to, is less than, let's say, it's less than the height of this barrier. So no matter how many times you push it through the cliff, it'll always fall back and will never cross that hill, right now. But classically speaking, it is true. Quantum, no. Let's see why. You see, when you go quantum, the nature of particles, the nature of matter, the nature of reality itself changes into something very non-intuitive. Matter starts acting like a wave function to be more precise. And if you would look into the classical mechanics of waves, simple regular mechanics of wave, you do realize that whenever a wave hits a barrier, unlike a particle, it doesn't stop there at that very moment. It doesn't stop immediately. It decreases exponentially. Its amplitude decreases exponentially. And sometimes when the barrier is thin enough, it manages to take its little peak out of the barrier. And the name is very beautiful and self-explanatory. Evanescent wave. I love that name. Now this is an evanescent wave that is being passed out of that barrier despite this wave function having less energy than that of a barrier. And that's beautiful, but we have to see what those wave functions actually define. What do we mean by having a wave function, leaving a speck of it at the other side of the barrier? You see, wave functions actually